This is actually the place when we stopped yesterday. I'm not sure I want to describe this again, but well, there are a few more things about these experiments which we found, except for these three, that we could stop a through flow due to gravity. So we stopped it just by external forcing in the axial direction. But okay, there are a few more effects we saw, but we did not document them in the paper because it was not that interesting. But maybe after, just when we finish, so maybe I will just describe a few more. But in any case, I think my last sentence, or one of the last sentences before we finished last time, was that I don't know why, what was the mechanism of sort of choking this flow, because we don't know. One of the guesses was, as I described, so I mean, in the forthcoming, actually in the subsequent efforts we made to derive lots different kinds of models just to fit these kind of features and to maybe to find a clue why it, this happened this way. So we derived all kinds of models which were based basically on the base flow, which was a Nusselt flow. But then we realized, and we failed. We succeeded to stabilize the liquid gas interface, make it flat in the cylindrical sense, okay? But we could not stop the flow. And then we realized that the Stokes layer thickness is about 5 times larger than the mean thickness of the film. Okay, so then you say, okay, so if this is the case, so let me find something around this slug flow, just like a flow with a uniform front, or with the uniform in the spanwise direction uniform velocity profile. But so far we have not succeeded to derive a self-consistent model based on this. So it's still continuing. Okay, anyway, based on all of these facts which I described yesterday related to these forced films and actually drops, so we thought that it might be nice, let me skip all of this, it would be nice to look at the case of a liquid film covering the outer wall of the cylindrical surface. And cylindrical surface for these efforts will be a horizontal one, not a vertical one, and to try to force the film through parametric excitation of the cylindrical surface, just forcing it in the axial direction with a certain frequency, certain amplitude, and see what's coming up. Okay, so basically, while looking at the faces of people here, so I understand that I don't need to invest too much time to introduce the Rayleigh instability or capillary instability of liquid column, let's say, or liquid jet. Just to mention it, are there any students here? Students in the sense of students?
There is one.
Oh, you are one. You are two. Sorry about it.
Yes, one more.
Okay. So, are you familiar with the Rayleigh instability?
Yes, familiar.
Oh, they're familiar. Okay, very good. So you can teach me now. Okay, fine. So basically, if you have a liquid, just a few words. If you have a liquid cylinder, so if it gets sufficiently long in the sense longer than pi times d. D is the diameter of the circle of the base. Okay, so if it gets larger than that, so then it will not remain just a cylinder, but it will break up. It will tend to break up into droplets, okay, due to what's known to be Rayleigh instability or capillary instability. So basically, if you have this guy and lambda is 2 pi over a k, k is the wave number of the disturbance, so there is a disturbance, and then what happens, you can describe the radius of the local radius of this body in this way, where okay, R, capital R is just a mean radius of the cylinder, and epsilon is just as the amplitude of this harmonic disturbance. So there is a competition. Actually, the Young-Laplace's equation or Young-Laplace law teaches us that the capillary effect is actually proportional to the mean curvature of the surface, and it has two components. It actually two principal curvatures. One of them is associated with this circumference, and this is K1 is 1 over R of Z, and R of Z is this guy. So for small epsilon, you can expand it into a Taylor series, you get this. But there is another one in the longitudinal direction, and this is a negative second derivative of the local radius with respect to Z. Z is the longitudinal, the axial direction, and actually you get for small, actually not only for small, but you can get this expression. And now the Young-Laplace equation says that the difference between the pressure inside and outside, let's call it P atmospheric, is proportional to sigma, actually equal to sigma times K1 plus K2. Okay, and what what happens now? So now if you have a thinner part and you have a thicker part, so it turns out that in the thinner part the pressure is larger than in the thicker part, just by looking at these two components, and then you realize that just this pressure difference between here and here drives the liquid from the thin part to the thick part. Now, in this case, the poorer people live at the expense of the thicker guys, and so it goes this way, so the thinner part becomes thinner. And this enhances the instability, so this the configuration gets larger distortion than before, and that's how it propels. Okay, by the way, so finally, if you start with the cylinder like this, so you end up with something like this. So your cylindrical column disintegrates into a series of droplets, and that's how it looks. Sometimes there are satellites, which means smaller droplets between the bigger ones. Sometimes there are not. It depends on the size of the domain. Anyway, this is the picture. Now, by the way, the price, I mean, if you look at these two components, you realize that for small epsilon, this guy is 1 over R. However, this guy is order epsilon. Okay, so we have here actually one order of magnitude in epsilon. One is bigger than the other one, and this actually it poses a headache in actually every kind of asymptotic expansions, like long wave expansions, when you try to deal with the problem in the long wave limit. Okay, so you have to keep both of them just because they are crucial for the balance, but they are several orders in epsilon apart. So this is a problem, and unfortunately. Anyway, okay, so now let's think about the following. Okay, we saw yesterday several examples of some very interesting phenomena which come as a result of external forcing of fluid systems. Okay, so here is one more in this gallery. Okay, imagine we have a horizontal cylinder. This is the cylinder. Somehow it looked a curve, but it's not. Okay, and you coat it with a liquid layer. Okay, thin liquid layer, and leave it as is. Don't do anything. Okay, so we understand that actually now there will be a combination of actually two effects. One of the effect will be the same as in the previous transparency slide, which is Rayleigh instability or capillary instability of the film. Actually, we talked about a liquid column, but if you coat a solid cylindrical surface with a liquid film, so you have the same thing. So the same forces will act in the same direction to your film, even axisymmetric, even flat in the cylindrical sense. Okay, it will not stay this way. It will go the same direction toward the breakup. Now the breakup may be a little bit slower because of the presence of the cylindrical core, but the destination will be the same. So final destination of this guy will be to rupture, not to maintain its contiguity. Okay, so definitely if you wait long, so this film will rupture. But there is another effect. We also discussed yesterday, this is Rayleigh-Taylor instability. So actually if you live in a gravity field, okay, so what happens that at least on the underside of the cylinder, you have the heavier fluid above the lighter one, the gas. Okay, so it will be the same effect like we discussed yesterday, 7 meters of water film on the ceiling. Okay, so it will want to rupture and to come down. But so it means that after some time, the breakup due to the Rayleigh instability and the Rayleigh-Taylor instability will bring water first to the underside of the cylinder, and then finally after some time you will see this. Okay, sort of array of droplets hanging from the ceiling, in this sense, the underside of the cylinder. However, now think about forcing this film by axial vibration of the film in the axial direction with let's start with the simplest case. You have just harmonic oscillation with one single frequency and a certain amplitude. Okay, so what happens? It turns out that this picture is replaced by this one. Okay, now what's the difference? The difference is that these guys, isolated droplets, if you don't do anything, so finally, actually there is a liquid bridge, actually a connecting between them. So once this bridge is ruptured, and I mean the droplets suck liquid into them, okay, on the expense of this liquid bridge. So finally, this drainage culminates in rupture of a film, and then a droplet just falls down, or maybe it becomes fat enough before and it falls down. Now, if you start oscillating this cylinder in the axial direction, so you see this picture. Now, next I will show you a movie, and actually this picture was taken from that movie. So you see first sort of elongation of droplets along the surface, and merging of the adjacent droplets. And an additional effect is that if you look at this configuration, it's definitely very much asymmetric with respect to the cylinder axis. Here, I don't claim that it becomes, you restore axial symmetry. No, by no means. But it becomes much more axisymmetric than in that unforced case. Okay, so, no, sorry. Yeah, this direction. Actually, that direction. Okay, good. So, okay, so now I have to use my finger as a remote control. Okay, so what you are going to see, sorry for the poor quality of the movie. We burned out this device before we knew how to shoot good movies. Okay, but I think it will be okay. Now, okay, so this is a cylinder, and this is beginning. Well, I hope you see. Do you see droplets here and here and here? So there are 5. 1, 2, 3, 4, 5. Okay? And this is a cylinder. Now you will start playing with it, oscillating it, forcing it in the axial direction. Now you will hear the noise. Don't be afraid. The noise is actually coming from this shaker from the movie. Okay? So it's the same device we used in the vertical case. So the frequency is constant. The frequency is 20 kilohertz, but the amplitude is between 0 and 120 microns. Okay, so the louder is the noise, it means that the amplitude of forcing is larger. Okay, but so we play with it. We'll see. We'll play with the noise, which means we play with the amplitude of the forcing, and going back and forth, so you'll see what happens with the droplets. Well, I hope you see. Do you hear noise? Maybe I should increase. Okay, you see the noise, I mean the amplitude gets larger and these guys are actually elongated along the cylinder. Okay, once we stop it, these guys come back over here and one of them just even it falls down, I think this one. Let's see. On which one do you bet? I think this one will. Okay, so finally this is the, exactly. Okay, my bet was correct. Okay, so you see what happens. I mean, this is kind of reversible effect in the sense it's non-linear phenomenon, but these guys come back at about the same position. So when your amplitude is sufficiently large, the droplets merge and are stretched, elongated, and it saves this stuff. Now I have an additional movie which is much shorter just because of the fact that we brought some a substitute for that broken device, but people say don't operate it for longer than 1 or 2 seconds, or 4 seconds, I don't remember, so that's what we did, but you see it's much better. Okay, it's not my finger. You see the same effect, but it's seen much better. Oh, the same guy fell down. Okay, so this is the effect, so we'd like to understand. Okay, what happens when you force the cylinder and what kind of effects you can get. Okay, so now the outline of what I'm going to talk. Now this part of this piece of work is done with Ori Haimovich, who was my master's student, master's degree student. Now he's a proud officer in the Israeli army. So this was actually part of, actually the major part of his thesis, and now you see that he keeps working even in the army. So basically, first I will describe the stability of the film of the isothermal force cylindrical surface in the single frequency case. And then I will try, time permitting, to discuss the double frequency case, which has some nice features, very unexpected ones. And then, again, time permitting, I will try just very briefly to touch the non-isothermal case. That's, a copy and paste. Okay, so this is just a sketch for the whole thing. The notation is just RC, that's cylinder radius. This is the film and the location of the interface. Of course, we understand that it will not remain axisymmetric flat in the cylindrical sense following this green line, so it will deform, and the location of the surface is given by this function h, which is in general depending on time, and okay, x, this is the axial direction, theta, which is the azimuthal angle, and okay, r, its location. So h0, that's the mean thickness of the film, and a whole bunch of properties. G is acting here. Now the forcing, as I said, single frequency case. So b is its amplitude. Omega is a frequency of the forcing, and the whole bunch of properties of the liquid standard notation. Okay. Now, what we did, we actually derived, we looked at the three-dimensional case. But the three-dimensional case, so we actually derived using methods I described yesterday and the day before. So we were able to derive the evolution equation governing the nonlinear evolution of the surface in the three-dimensional case. A three-dimensional case means, three-dimensional physics means that your evolution equation incorporates the dependency on actually two spatial coordinates, one axial one and the other one is the azimuthal one. But the equation looks bulky. I would not even attempt to present it here. Well, it's not that bad, but it's sufficiently bad. So, and our computational power, even now, I don't think that it's enough to explore in full what we got. So that's why we said, okay, let's settle down just for a simpler case, one-dimensional physics. Sorry, two-dimensional physics, which means one-dimensional equation, which means the axisymmetric case. But to our big luck, we know that, and actually it was shown experimentally also by De Bruyne some 15 years ago, or now it's 16 years ago, that if the bond number, I don't remember, I think I introduced it yesterday, or yeah. But anyway, okay, let me forget about bond number. If both the mean film thickness and the radius of the cylinder are much smaller than the capillary length of the liquid, which is this value, okay, so then you may say for sure that gravity effect is dominated by capillarity. So it does not mean actually that you can forget about gravity. You can, you may. But the question, the real issue is the following. Are we still able to assume that the axisymmetric case is valid? Well, because if you don't have gravity, so there is no factor which pulls liquid on to the underside of the liquid. But it still does not mean that the flow will be axisymmetric. It may be non-axisymmetric by itself, not only because of gravity. Okay, so to defend ourselves, so we have two things to say, actually more. One is if you take the full equation which is derived for the general case, non-axisymmetric case, and assume the bond number is to be small. And then you expand everything, including the location of the interface, in the Taylor series with respect to the bond number. Then you find that the lowest order of this, you find the axisymmetric problem. And then the next order of this in bond number, the problem will be, again, well, now it will be non-homogeneous in some sense, where the forcing will become actually will emerge from the lowest order. So actually at main order, at the lowest order of these expansions, or with respect to the bond number, it's certainly axisymmetric. Second, I must say the following, that actually the flow may be non-axisymmetric. So if you look at the linear stability analysis for the problem, you find that the fastest growing linear mode is actually axisymmetric. Okay, it loses first in stability. Okay, so which means that one more, a credit for you just to talk about the axisymmetric case. It still does not mean that non-axisymmetric mode will not appear in the nonlinear stage. To know that for sure, you must solve the full equation and then speculate this way or that way. Okay, so what I'm saying is the following. Let me start with, is that what I told him? Start with the axisymmetric case. It's better to solve something that, runs computations for non-axisymmetric case and be waiting for several years before this computation is over. Okay, so let me begin with the axisymmetric case. We did start to work on the non-axisymmetric case, but again, now we feel that the computation power is still not sufficient for that, at least in my lab. Okay, so I don't want to go through the equations. Let me just look at the long wave limit. Again, we'll define the small parameter epsilon as the ratio between the mean thickness of the film and the typical wavelength of the disturbance. And again, as I say, we look at the axisymmetric case and scale in the standard way all the variables and find that we have four non-dimensional parameters. Okay, let me start with this guy. It's a capillary number, actually inverse capillary number. This one, we call it geometrical parameter, which is the ratio between the thickness of the film and the radius of the cylinder. And then we have two dimensionless parameters for forcing. This is the dimensionless amplitude, and this one is dimensionless frequency. It looks like, well, some people call it, it's a Womersley number. it's sort of the ratio between or the square of the ratio between the thickness of the film and the viscous, actually Stokes viscous layer. Okay, so that's how it goes. And we'll assume that H is order 1, although numerically small. Okay, so we are talking about low frequency limit, and this we refer to the low frequency limit as to a limit where this value is order 1. Omega, remember from the previous slide, is dimensionless frequency. So this means that the frequency is dimensionless frequency is small. If you go to a different limit, which is high frequency limit, that's a case you discussed and you, Sergey, discussed with Michael. That's where you do separation between different time scales and okay, average the equations and separate into pulsating parts, averaging part. There is no such approach here because it's low frequency limit. So we have slowly varying in time everything. Okay, so that's why we have the slow times. That's exactly the time, the typical time for long wave limit. Okay, so after some struggling with everything, we could and we could not, and we have some reservations about some asymptotics there. That's why we wanted to find some, you know, some external expert opinion, like solving the same problem but not using a long wave theory, but just solving Navier-Stokes equations with brute force or some other force, okay, heavenly force. Anyway, so just to compare. But basically, the final equation to look at, it's a guy shown here. So let me explain what you see here. G, this G is not G, which we think a gravity. Gravity is long forgotten, right? G is this guy. And the reason is to write the equation in a somewhat ugly form is the following. Okay, thank you very much. Thank you. So the equation for H was something like this. H1 plus HT, okay, equal to something. Now, for numerics, it's definitely a very big advantage if you rewrite or recast your equation in the conservative form. So you want to write your equation in the form something like GT, it doesn't matter what is G, equals or plus DZ. Okay, so Z and X will be interchangeably, I mean, the axial direction. Sorry about that. dz of something equal to 0. Okay, so numerics is definitely much better run in this case, because then if you write your equation or rewrite your equation in this form, in the conservative form, it means that you can check mass conservation. And if your mass conservation is not good for you, so then you reduce, either you reduce the time step or you increase the number of grid points just to have your mass conservation at a certain level. But here it's very, very easy, because you can write this as dt of, okay, what's written there? 1/2 of h squared plus hh. That's exactly this. So that's why it's written for this g, but the price to be paid, the curvature term, where it's here. It looks much uglier than it should be in reality, okay? That's because of this transformation. But anyway, it can be handled numerically. Okay, so what you see here is the following. This guy and gamma function is this one. Okay, so what is gamma? Well, it's very hard to recognize, but I will tell you what it is. This is a remnant of, a reminiscent of the exact solution of the Navier-Stokes equation when you have an axisymmetric flow along the cylindrical axis. Okay, remember there was some logarithm there. It's exactly this one. If you have a flow in an annular gap. Okay, so that's exactly this. because of this transformation, it looks a little different, but that's about the same thing. Okay, so this term is associated, of course, with a curvature of the surface, more precisely its longitudinal derivative. So that's what you have. If you don't have any forcing, so B is 0, so this one goes away, this one goes away, you are left with this guy. And actually, if this guy H goes to 0, then you get the equation coming from Hammond paper. Let me write it, and then you will immediately recognize that we know it from somewhere. It will be something like h cubed hxx plus h cubed h. Well, it will not be the same h. Let me call it this way. Okay, if you look at this equation, so that's what happens if this h is sent to 0. Okay, so this equation, if you look at it, that you recognize that we discussed this equation yesterday in the absolutely different context. The context was Rayleigh-Taylor instability. Remember 7 meters of water on the ceiling, so, or maybe 8. Okay, so that's exactly the same equation. So which means that this guy knows, so the competition between the two components of a curvature, okay, act in some way. One is stabilizing, the other one is destabilizing. So the destabilizing curvature in the circumferential direction is this guy, and this guy is due to the capillarity, to the stabilizing part of the capillarity along the axis. Okay, now, okay, if B is non-zero, so we have two terms. One is here, one is here. This one is linear one in G. Which means that if you forget about this guy, what do we have here? You have here linear wave equation. So it goes, periodically it goes one way and then it comes back just according to this sine omega t. So it doesn't know where to go. So first it goes this way, that way. It oscillates, doesn't do anything because actually you can scale it out just by going into moving frame of reference, so you will forget about this, you will not see it anymore. However, this one is very important. This one is nonlinear in G, same gamma function, okay? Gamma of G. So this one is nonlinear with respect to G, and it has some periodic variation with time, okay? So this might be a good candidate to explore its action, its influence on what's going on, and all the effects which we'll see there, which we'll see here. Next, they are mainly produced by the competition between the two, but mainly they are produced by this guy. This is the main effect of this vibration and not this one. This one will do just a translation, but not more.
Alex,
yeah.
How can the phase shift be explained? What is the phase shift of?
You mean here?
No, cosine of omega t.
Yeah, and sine. Well, because you see, this guy comes from, okay, so I forgot to tell the following. We assume that the Reynolds number is based on the, actually the atypical velocity is related to this forcing. So which means that, frankly speaking, Reynolds number in this sense is 1. Okay, that's why you didn't see it in the list. Okay, so which means that we want to keep the lowest order of advection in the equation, in the effect. Okay, so which means that, and the nonlinearity there will bring up this effect. Okay, so that's why this guy is nonlinear, but this one is linear because it has also WT, and WT will be linear with G, but this one is WW, so that's why it will come from there. Okay. Okay, so just to make life easier, we say let's just test the equations for the following physical example. So we'll take silicon oil, just fix the properties just to make sure that everything except for forcing parameters, everything is fixed. Okay, so okay, and we take H0 0.1 of millimeter, the thickness of the film, and the radius 0.5 of millimeter, and compare it. Remember, we have to comply with the requirement that both of them should be much smaller than the radius of the cylinder. In other words, the bond number should be much smaller than 1. Okay, so for this guy, the capillary length is about 1.5 of millimeter. Well, I don't know how much smaller 0.5 is with respect to 1.5, but well, at least 3 times. Okay, and of course in the equations there is one more additional parameter. Sorry, this is this guy, okay, L, and L is just the periodicity of the domain, because we are going to solve the equation in periodic domain. So periodicity, it comes as a punishment for our inability to solve the problem in the infinite domain. Okay, so you have to pay the price and to add one more parameter. Okay, so okay, before we speak about vibration case, let's talk a little bit about non-vibrating case, or unforced case. Okay, so here it is. Okay. Okay, so we'll start with no vibration case. And this graph actually shows you, okay, H, which is the mean, by the way, the equation was solved for G. And then once you get your solution for G, so you recalculate it through this. This is actually G, so it's monotonic function, so there is one-to-one correspondence between G and H. And we show H. Okay, so this is H as a function of the longitudinal direction, of the longitudinal Z or X, or one of them a variable. Okay, and what you see here, many curves, so they are corresponding to different times. So there is the evolution in time of the interfacial shape. So for example, the black curve is very close, it's almost the initial condition, so it's sort of a periodic function of the Z. And as time goes by, follow from the black one to this pink one, and then it deforms, and then the violet one, and as time goes by, so you get to 1500, and at 1500 you see this blue curve. What you see here, you see actually a large drop in height, but if you look here, you see at 1, 2, 3, 4, maybe 5, 6, 6, about 8 places where the local thickness becomes very small. So actually, the film wants to rupture, exactly like we predicted with this breakup into droplets. So it's not surprising. And now, actually, if you look at the time variation of the minimal thickness of the film as function of time, so it goes very quickly down, and then it goes very slowly, but monotonically it approaches 0. Okay, so which means actually for this equation, it can be mathematically proved that the rupture is at infinite time. Infinite time means it will take you infinite time to get to 0 thickness. It doesn't mean it will get you an infinite time to get to a small thickness. No, you see it goes not fast, but sufficiently fast, goes to 0. And then you may say, okay, then van der Waals will ask for the price and will rupture you if it's attractive van der Waals, but if it's repulsive one, so it will create kind of adsorbed layer, which for any purpose may be also called macroscopically ruptured. Well, anyway, this is not new, and this is definitely is expected, this kind of rupture. Okay, now let's see what happens in the vibrating case. In the vibrating case, the situation is quite interesting. Why it's interesting? Because we find, okay, this is the plane spanned by the 2 forcing parameters. This is omega and this is b, okay? And of course, as we saw, if b equal to 0, b equals 0 means no forcing. Okay, so b equals 0 is along this one, so you expect rupture as you saw. It turns out that in the forced case, there is a line demarcating between the 2 regimes. One regime below it, okay, adjacent to b equals 0 regime, that's where a rupture takes place. No matter whether you force it or not, a rupture will come. slower or faster. We don't know why. Sometimes it's slower, sometimes it's faster. You will see next. But it goes over there. On the other side of this curve, there is no rupture. So you sustain the continuity of the film forever, or at least as long as your computer is alive, because once you don't pay your electricity bill, so you don't know what happens next. Okay? But anyway, but what is interesting is the following. Based on similarity arguments, what I call numerically assisted similarity arguments, we find that this curve is nothing less and nothing more than b omega equal constant. Okay? Very simple hyperbola. Why I say it's numerically assisted similarity arguments? Because there are similarity arguments. Just looking at the value, at the units of all of these guys playing there. But we have two constants which we don't know, two powers, and we have only one equation relating between them. Okay, so we have to find an extra information from somewhere, and this somewhere is our numerical computation. So once we see something following a certain law, so we know that a constant, we substitute it here, and that's what we find. Okay, so which means that and one more important thing, not less important, that this constant is independent of the forcing parameters. So it depends on the liquid properties, it depends on geometrical property, like this capital H parameter, the ratio between the thickness and the radius, but not on B and omega. Okay, and if you look at this relation, so you recall that in the case of the inverted pendulum we discussed briefly yesterday, so I said that you can stabilize the broom, you know, upright in the upright position if you oscillate it, provided that the product between the product of the amplitude of vibration and the frequency exceeds a certain value. Okay, there you stabilize it. Here you don't stabilize because it's linearly unstable. However, you saturate the instability. Okay, so the role of this expression is different here and there, but the form of this is very similar. So basically, if you exceed this value, this a constant value, if you are here, so you save the continuity of the film. Okay, so how it looks like? It looks like this. What you see here, this is again temporal dependence of the minimal thickness of the film for, okay, everything is fixed. Okay, H is 0.2. Remember 0.1 millimeter versus 0.5 millimeter. This is the capillary, the inverse capillary number. This is the frequency of oscillation, 2 pi. This the simplest case, right? And for various values of B. Okay, so B, look what happens. Many colors are present here. And actually, the rupture time is quite non-monotonic with B. But what's interesting for this and this and this case, three cases corresponding to the largest values of B, okay, everything else goes to 0. So which means at some moment the film will rupture, sooner or later. Here, it seems to live forever. Okay, so it's sort of a constant. Why it's sort of a constant, I will tell you immediately. But it looks like it's sort of horizontal line which lives forever. Now, this value, by the way, somewhere between 6.35 and 45, if you look at this graph, at 2 pi, it's what, about 6 point something, somewhere, okay? So 6.4, it's somewhere here. Okay, good. Okay. So now I said that there are some problems with with asymptotic expansions, when you have to take some decision which you don't like it, but unless you take it, you make this decision or that decision. So you have to support it by something, and you don't have too much support except for in the sense that you know what you should have in your equation, but it's very hard to get to. Okay, so that's why you want a second opinion from the independent place. And fortunately, we found this support from guys. These are the names. This guy just finished his master's degree in Germany, in Aachen. And they developed a code which solves Navier-Stokes equations. Okay, and when I was visiting Aachen, so I gave a talk, and they said, "Oh, we want to solve this." I said, "Okay, go ahead, do it." It took them certainly more than a year to make this code working for the problem at hand. Now, their code is still kind of is very unstable in the sense that sometimes they feel they need to increase the mesh and to put more grid points and to maybe to run it slower in time, but they cannot because it will last forever. Maybe this guy would have finished his master's degree maybe in 5 years from now, but he has no time. So let's see what's going on. And then they said, okay, we can solve one case for a half of your periodic domain, and let's see what happens. So what they found, again, this is, well, different notation, but that's exactly the same, the temporal variation of the minimal thickness of the film. Now, this is A bar, it's the same B. In my case, it's 0. If you follow this guy, so it goes to 0. Well, it should be run more, but that's where they stopped it. Okay, now, okay, this one, A is 1.59 something, so this guy, so it goes to 0 much slower, but it goes. They run it further, and it goes here towards 0. However, this one, 3.18, it stays away, and it's already a few months later, and it's still far away. It's about the same value, so it follows the same pattern. Now the question is, okay, how these numbers are related to our numbers? Well, for us, I asked my student to run it for this case, and he ran it. It took him maybe a few hours, and then he said, okay, so our critical value for this case, it's not 6.4 because it's half domain, so the value should be different. It's 2.42. Okay, so 2.42. These guys said it's 2.57 because they said, okay, slightly above this one, it goes to 0, and slightly above it, it stays away. So they're still running, but it seems to, at least this variation is number-wise very, very similar between the two. So that's why we got even more confidence in the results. And okay, so they are proceeding with their numerical computation. Okay, what else? Okay, so okay, now I would like, so I know that I can preserve the continuity of the film. So now I want to see how the interface evolves. Okay, so this is one of the cases. Again, this is 2 pi, the same values for this, because these are actually fixed. We play with this omega and b. Okay, so this value is for this case, for this one, Okay, so beginning with some initial condition. So this is, okay, the early stage of the evolution. Now you see development of all kinds of ridges, all kinds of droplets. And then between 100 and 1400, that's how it evolves. This is 100, exactly this one. And then it evolves. And then it looks like between 500 and 1400, it stays here without moving. Okay, and then you say, oh, I reached the steady state. But it sounds a little odd, that you oscillate the system and it stays at the same location. And the reason is it stays at the same location because I'm a little cheating you now, just slightly. Why? Because I'm showing you the profiles only for integer times. Okay. Now look at the frequency is 2 pi, so the period is 1. Okay. So assuming that the flow is periodic and the time periodicity is exactly connected to the forcing periodicity, so I'm just stroboscopically sampling something without telling you more information what happens within one period. Okay, so we all understand this. It's called white lie. Okay, and now we'll see what happens within one period. Okay, so the one period here it's exactly between 1400 and 1401. Sorry for the mess, but I will explain you what's going on. Okay, so we take the film at this time, and the location of this guy, this is this fat black curve. Okay, this is the beginning of the story. Okay, so now remember how sine looks like? Sine looks like sorry for this, but that's how it looks like. This is sine, no, this is t and this is sine omega t. Doesn't matter what is omega, okay? So it means that if you follow this line, so first you go up and then for the first quarter period and then for the next 2 quarters period, you go down and then again, finally you go up. Okay, fine. So, okay, having this in mind, okay, look now, okay, start with this and look at the dashed curves. So during the first quarter period, this guy follows these dashed curves. So first it looks like this, and then it looks something like this, and then like this, okay? So it goes to the left in this sense, okay? Now, okay, solid curves are for the second quarter period. So what you see is they go in this direction, exactly like this guy. And then for the third quarter of period, again, they're still solid, so they go in this direction. And then finally, they go with this type of notation, so they go to the left. Finally, at time 1401, they get exactly to the same fat curve as we had in the beginning. So which means that there are a few more features, I will address them as well. So what happens is that the evolution is time periodic. The periodicity is exactly like the periodicity of external forcing, and that's what happens. Now, how about the minimal thickness of the film? I said that it looks like a flat line, nothing happens. No, things do happen. Look here. Look here. Okay? So it's definitely not a constant. And why is that? Okay. The reason is the following. Imagine, so the equation, well, I didn't write it here. Remember the equation in the nonlinear okay, term. That's exactly the term you asked about why it's a cosine. Okay, so this term twice per period is 0. At certain times it's 0. A cosine omega t twice per period gets through 0. Okay. Now, if it gets through 0, effectively it means instantaneously b is 0. If b is 0, so this guy is vanished. If b is 0, what our film wants to do, it wants to rupture. Okay? It says, okay, that's my opportunity to rupture. B is 0, this guy is 0, let me do it. No, I cannot do it because then the next time you bring water, and this is absolutely inertial effect. You bring water, you put it in the thinnest location, the guy can forget about rupture until the next 0. That's why we see this kind of oscillation here, and that's exactly why that curve, which looked precisely flat, no, it's not flat, it's oscillating about a certain value, okay, just because of this. Now, okay, also, if you look at this blob, at this cloud of curves, you see the following. Here is the surface of the cylinder. So if you force your cylinder, so you drag your liquid over there, that's your forcing you put in your system, okay? So you drag the cylinder. Now, who are the liquid particles which sense more this forcing? Of course, those guys who live nearby. Those guys who live on the outer side of the film, okay, they feel it less. They feel these guys want to do something, let me do something similar, okay? So that's why here we have a very small, with, okay, respectively to the outer part, okay, amplitude of displacement. So they follow, this is about twice the displacement amplitude of the cylinder. However, at the outside, it acts like a jellyfish. Okay, so it goes, see the span of this vibration. So it vibrates much more, the displacement is much larger there than next to the surface. Okay, it's the same, but now I just make another projection. So you see time is going in this direction, and all of these guys are shifted by a certain amount just to see how it looks like. So we start with this one. So this hump goes in this direction, and then it goes in that direction, continues periodically from here, and then finally it goes there, finally it reaches its final destination, which is exactly like this. Okay, so it's a periodicity, and time periodicity of the evolution is exactly time periodicity of forcing. And this is another proof that it's a time periodic flow. So what you see here, you see actually phase plane portrait. DH is sort of HT, but it's numerical. Okay, numerically calculated, so there is an error of order delta t. It's a first order approximation even. Okay, so what happens that here we have 200 periods of forcing in these curves and in 3 different locations along the period. So it's clearly, I mean, the shape is different, but it follows the same pattern at the same locations, the same pattern. So it's time periodic. Let me skip this, let me skip this. Okay, interesting thing is the following. Now let's look at topological transitions with an increase in the amplitude of forcing, okay? So what happens for b equals 0, I forgot to mention, but that's, now it's not too late. For b equals 0 for these parameters we took, so there are 6 non-linearly, sorry, 6 linearly unstable modes in that period. We wanted to make it larger, but we also have to pay a price. So we made a compromise between sufficiently long and not too long domain. So there are six linearly unstable modes, and the fastest growing one, it's 6 divided by square root of actually 2, so it's 4. Okay, so that's why you see 4 big humps. There are some little satellite between them. That's exactly what you saw in the picture, which I showed you, the breakup of this liquid web, so to speak. Sometimes there are satellites, sometimes they are so small they are not discernible. So anyway, this is b equals 0. Now when you raise b, but still it ruptures, look what happens. These satellites disappear, right? You still have 4, and then you go here, you have 3 big ones. This one is the same like this one because it's periodic, right? But there are some satellites. Now the number of big guys decreases, and finally, okay, this is still rupture, so it ruptures. It's the same way like this one, non-ruptured, but it has only one drop, and there is a characteristic horn here, but it doesn't do anything. So the rupture, which means that actually if you drive this system back and forth, so your expectation, and you saw this in the movie, so there is a tendency to merge for these droplets. Okay, so this is sort of effect when at the end of day, if you prevent rupture, what you are expecting to see, from my perspective, is that just one long something without any identity for separate droplets. So it will be something like, like this. Can you identify here any drop? No, there are some humps, there are some troughs, but nothing more. Not, droplets without identity. They are all mixed together. So that's a tendency. By the way, I should be fair to say the following: in those brute force Navier-Stokes computations by these German guys, at this stage they don't see this decrease. They do see the decrease. They do see that the number, well, they cannot run for a long domain, so they run for a short domain. So they started with a domain when they had 3 nonlinear stable modes. So the second one was the fastest one. So it decreases with B, and actually the little hump, so there is a little hump, it decreases with B, but at this stage it has not disappeared, so we don't know yet what might be the nature of this discrepancy. Well, after all, it may be discrepancy due to the fact that this is asymptotic approximation, and that one is sort of original equation. You don't know, whether the numerical convergence has been achieved or not, but this is the situation.
Alex,
Yes, please.
looks like the front is steepening on the left. So the left slope is higher than the right slope.
And you ask why?
Do you see any tendency for the breakup? Of course, because you use the H equation, you can't see any.
You are right. No, yeah, well, we declare a breakup. I will tell you, okay, I also forgot to say. No. We declare a rupture when actually, don't forget that the physical thickness of the initial film was 0.1 of millimeter, okay, which is 10 to minus 4 of meter, right? Now, 10 to minus 7 of meter, which is 100 nanometers, that's actually where van der Waals, that's a playground for van der Waals, okay? So which means we declare a rupture when we get 0.001 in value of the minimal thickness, and 0.001 exactly means if you start from 1, which corresponds to 10 to minus 4 of meter, you reach 10 to minus 7, okay? So this is the criterion for rupture here. Now, back to your question. Maybe that's what you see it, but the point is that at which moment you want to take picture of this rupture, okay? So we took it just before rupture, okay? So which means if you look at it, because actually if the gradient is a little steeper on the left-hand side, it means in this very moment these guys were moving in this direction and not in this direction. If you would wait for another half period, so they will revert the direction, and the gradient will be reverted. So that's how it goes. Okay. What happens with time? It goes still monotonically? Yeah.
30 minutes, I think.
Yeah, about
30 minutes.
Shall we continue? Sure. Yeah. Okay. I'm fine. Okay, so let me look at the double frequency case. It's kind of exciting, more exciting. Okay, so now the forcing is described by this expression for the axial velocity component. Okay, so there are 2 frequencies, omega. Okay, let me start here. Okay, gamma is the ratio of two forcing amplitudes. Okay, it's been defined in the way that the smallest one divided by the biggest one. Okay, so that's why it's between 0 and 1. Now he is the ratio of forcing frequencies exactly in the same direction. Okay, this divided by z. Okay, so that's why we have two frequencies, omega and omega chi. We have two amplitudes, b omega, which is taken outside, but in return we have here gamma, the ratio of forcing amplitude, and we may have phase shift. That's how it goes. Okay, now, the same procedure, a little bit bulkier, but basically the same G. It's exactly this. If you open the brackets and cancel one, you get exactly here. And here is the equation. It's even uglier than before, but well, not too much uglier. Okay, so now we have two terms, actually four terms arising from forcing. So two of them are linear in G. That's exactly what we had, one linear term in a single frequency case, but now we cannot eliminate both of them. We can eliminate just one. The second one will remain. And two nonlinear terms in G, where they are hiding, yeah, these guys, multiplied by this gamma 1 function. Why it's gamma 1? Because initially there was another one, so we did something with that. Okay. So now we want to solve this equation. Okay, so first, a trivial case, sorry for trivialities, but before we go into complicated things. He is one. He is one means you force the system with the same frequency. There might be some phase shift, but essentially the same frequency. But the amplitudes are different. Okay, so now what would we expecting in the simplest case? If phi is 0, if there is no phase shift, and gamma is 1, no, sorry, if phi is pi, so there is a half period shift, okay? So these guys are canceling each other. So that's why this is a critical B. Now the critical B, that's exactly, this is omega, this is B, this is this hyperbola. So this is B equals BC, a critical value of the amplitude for a given frequency. Okay, so definitely for this competing case, we have BC is actually infinity. You can never stabilize it because you have effectively you have no forcing. These guys are just canceling each other. But then you see if for different values of gamma, you see if you approach phi equal pi, so it means that these two forcing components compete each other. So that's why you need a higher value for the amplitude to stabilize. Sorry, not to stabilize, to saturate instability. But this is less important. Let me skip this. Okay. So now the case of the general chi. Okay, what I'm showing here is the following. This is the value of chi, and this is the value of this critical amplitude of forcing. And okay, the parameters are fixed. C is fixed, H is fixed, everything is fixed, omega is fixed, B is not fixed, of course, and but gamma changes. Okay. And then we run a cloud of computations for each case to locate where this critical B is located. So now what can you see here? Well, basically, as we expect, okay, things must decay. The larger frequency means larger decay or faster decay, but there are some spikes here. Okay, which actually drove us crazy for several months, I think. And I said, no, something is wrong, run it again, run it again, run it again. And said, no, I run it again, it's still there. And what's more interesting, it's kind of point-wise spikes. It's not like a domain. It's very localized effect. But when we run for more and more values of gamma, look what happens. The location of all of these guys, it's almost the same. It's actually the same. It's actually the same. Okay, let me tell you. This is 0.5. That's okay, that's a riddle. This one is 0.5. This one is 0.6. Well, there is some minor here, I'm not sure about this. This one is 1.4, and this one is 1.5, and this one is, of course, 2. What is common between all of these numbers? And what is common is the following. 0.5, okay, sorry for arithmetics. It's 1 divided by 2. 0.6, it's 2 divided by 3. No, it's 3 divided by 5. Yeah, exactly. 1.4 is it's 7 divided by 5. 1.5, it's 3 over 2, and 2 is, well, sorry about trivial things, 2 divided by 1. So it looks like we can quantify these numbers just as sort of ratios between sort of narrow band primary numbers. So which suggests in some sense, so there is some subharmonics which are floating around in some intricate way. Okay? So still, we would like to have an explanation for these effects, actually this effect. And it took us another few months just to figure out what's going on. Okay, and actually here is the story. From the previous case, from the case of a single frequency, we say the following. Just by looking at this, and remember this is b omega equal constant, we can speculate that the matter whether the film is saturated or not depends on the value of the maximal velocity, or it's sort of either maximal or minimal because it's harmonic, of the maximal velocity of imparted by forcing. B is the amplitude, omega is 1 over time, right? So b omega is sort of velocity. So the maximal velocity, if the maximal velocity exceeds a certain value, bigger than this const, which is independent of forcing parameters, so you save your life, okay, or the film's life. So based on that, and based on the fact that this phenomenon seems to be independent of gamma. For all of these gammas and for others, we run for 6 more, I think. To generate a curve like this, it takes, I don't know, a week or something like this. Okay, so we found that all of these spikes were located at the same location. Okay, so what we say is the following. The location of these spikes is probably, depends probably solely on chi and not on gamma, because gamma doesn't play any role here. Okay, so based on that, we say, okay, so here is W. W is, W, where is W? Wow, that long. Is so we rewrite it in the dimensionless form. And then we say, okay, let's try to maximize or to minimize this W as a function of chi. And we get some transcendental equation which we cannot solve analytically, but we find large time solutions, and these are phis like this. We find some maximum of maximum, maximize, and finally we say that the location of these extremal values for W, they correspond to the maximal value of this expression where phi n is this with respect to n. Okay, and then we say, okay, let's plot this value as a function of chi, so that we find something like this. Okay, and then we say, okay, let's compare. Okay, here we are. 0.5, 0.6, 1.4, 1.5, 2. That's exactly, these are locations. We cannot explain why some others minor guys appear there, I don't know. But it seems like we found the location. We could fish these guys one by one, just say, okay, this one should be staying there, and that's what we find. The correspondence between the numerics based on numerical solution of that evolution equation and the location of these specific points is the same. Okay, actually, this is the case for, and this is for phi equals 0. So there is no shift, phase shift here, phi equals 0. For any phi you find, you look at, you find something similar. Now, one more thing I wanted to address here. Okay, and finally, I still have some time, right? Oh, okay, so now I feel rich. Okay, so now I can speak slower. Okay. Okay. Before I spoke supersonically, now I will talk subsonically. Okay, so now let's think about the following case. Let's think about the single frequency case. But let's assume that there is a little temporal modulation of the amplitude of this single frequency case. So which means, let's assume that the forcing looks like this. This is the base frequency of our forcing, and this beta, this is associated with the modulation of the amplitude. Okay? So let's assume that beta is smaller than 1. It's positive but smaller than 1, so it means that the modulation is slower than the forcing provided by the main thing. And let's see what happens. Well, you don't need to have a very deep knowledge in a trigo to understand that it's related to the single frequency case, double frequency case. So you can write this exactly like this, where all of these guys are here, and go back actually to your double frequency case, which was discussed just a few nanoseconds ago. Okay, so what happens here? Okay, so let me look at this value, okay, m. Actually, m is max minus mean of h. So the film is followed in the periodic domain, and that every time, every moment, I watch for the maximal value of h and the minimal value of h. They are not in the same location, of course. And let me subtract this from that. So it's so-called peak-to-peak size of this wave, of this pattern. Okay, and let me plot it as a function of time. Okay, so basically this you know already. It's not different because beta equal to 0. Okay, so there is no modulation actually in this case. We are back to square one, back to the standard single frequency case. So it looks like, look at the values of this m. So it's between, I don't know what, 1.4 to 1.45, roughly speaking. Okay, so there is a variation, but the variation is not really exciting, nothing to write home about. Okay, and it goes periodically, as we know, with a period specified from, what is omega? Omega is 4 pi, so a period is 1/2. Okay, not big deal. However, now let me take beta non-zero. Let me take it small value, 0.0, actually 5 times 10 to minus 4. Okay, so which means I have long wave modulation in the temporal sense, long wave modulation of the single frequency case. So what can I expect? And that's what I expect. I look at the same value of m, and this is time, and everything is the same except for, I don't remember, b. Yeah, b is the same, again, a 3.3. Okay, it's the same. But beta now is non-zero. Look what happens with this poor m. It goes not between 1.4 and 1.45. Look at what happens. It goes almost up to 5. Okay, so, and it goes periodically, by the way, and a period is associated with, oh, by the way, the period is associated with the slow modulation of this forcing amplitude. And of course, look what happens here. The pattern looks very much different. There is a tall guy at the times corresponding to these peaks, okay? And then it subsides, and then this guy get more water, but at one period after that, it becomes again there is a sort of splash. And this is actually we thought about this, and it looks like we found a sort of right connotation or right analogy. Think about musics. Think about two instruments which are, I mean, two players want to tune their instruments to play at least the same way, okay? So they wanted to tune the instruments, and then at some stage you hear an incredible noise. Okay, it happens exactly when they come very close each to other, so there is some sort of resonance. It's not resonance, but it's, I mean, there is a surge of the sound, and then it subsides when they move closer, okay? And in acoustics, it has its own name. It's called beating, okay? So there is this beating or beats, so it looks like that's exactly the same or similar. Okay, these are spikes when you have a surge in the volume and then it subsides. Okay, so it's kind of reminiscent of that. Okay. There is one more issue which is not completely clear. That's why I wanted to bring it to your attention. It's not clear to us even after the paper is accepted, and so we're still thinking what's going on here. Well, yeah, but science is all about thinking, rethinking, and like a cow, it doesn't eat at one stage like we do, okay? It's double stage, a process, okay? So maybe at some stage we'll understand this. Anyway, look what happens. I have, again, this amplitude modulation case, and I plot now, okay, xi or xi, which is a maximal value of this m, which we showed before. What's the difference? Again, okay, m is at any time, specific time, I look at the peak-to-peak size of the pattern. But this is a function of actually time, right? So that's why it varies, okay? Now I solve the equation and I look for the maximal value for all times of this value m, and I call it xi. Over here. It's actually, it's written, yeah, it's here. Okay, and I wait upon saturation. So I want to be beyond this, the transient process, so I want to be at the saturated state where everything is already settled down. I don't want to remember what happens just right after this guy departed from the initial condition, okay? And, okay, so this is a case of beta equal, yeah, this is beta. Beta, this is the wave number of the modulation, okay? So for beta equals 0, for these two values, so I'm already saturated for this omega. Omega is 4 pi. If you remember 6.4 for actually 2 pi, so for 4 pi it should be twice smaller, okay? So it should be 1/2, 3.2. So I take 3.3 and 4. So both of them are above saturation level, so it should be. So for beta equals 0, so I have this xi, these two distinct values. Now let me start with large beta, okay? Large beta is over there, so I modulate this single frequency case and record the value for xi. So it goes like, it looks like for sufficiently large beta is a constant value, okay? So it doesn't make any big difference. However, when beta becomes large, sufficiently small, this guy xi starts climbing for both of these values, okay? The red points are for 4, and this one is for 3, okay? So they go up. So up to 0. So last time we caught them numerically, it's somewhere around that value which I showed you, these tall peaks with m going almost up to 5. And then nothing. Why nothing? Because after we pass this value, it looks like it ruptures. So it never, I mean, so the forcing amplitude must be much larger than these values to arrest rupture. So it looks like, but I'm sure this is absolutely numerical effect, which means that numerically we are somehow unable to capture it. It looks like the case of beta equals 0, it's sort of singular location, and then there is a gap between 0 and this value, which is small but non-zero, okay, where we can follow this kind of saturation, okay? So this point is actually, well, somehow I don't like it, and I still think about this, and my student is thinking about this. So it looks like there might be, just a conjecture, there might be some asymptotic expansion which might, for small beta, which might, okay, hint what's going on there, but the difficulty is that time is involved, okay? And if you have, I don't know, sine of beta omega t, what can you expand for small beta, because you have a t for a long time, so small beta means nothing, okay? So this is the point which I don't know what is it. If you have any ideas.
But it can depend on the threshold value of the thickness. Below that, you think that the film is rough.
No, it doesn't seem so, because once I get to 10 to minus 3, frankly speaking, even if my numerics is very careful, okay, I mean, I would not believe in the solutions which leave the brink of 10 to minus 7, and I have to decide whether it should be alive or dead. It's maybe.
At least there is some kind of explanation for that. Maybe I just invented.
Yeah, I see.
It's wrong.
No.
You see, decreasing this beta, you have a larger time between these two pies.
Absolutely.
During this larger time, your film can rupture, and it goes lower and lower.
Right.
And perhaps allowing it to go beyond this threshold, you will show again, not rupture, but again the pipe.
Okay. Maybe. My explanation I gave to my student maybe is not good, but let me share my views with that. I told him, look, you may believe your numerics or you may not believe, but when I see structures like this, okay, look at the amplitude 5, okay, so my feeling is the following. So actually, if I go to the left on that graph for smaller beta, okay, so it actually means that this amplitude goes up, okay? So how come, I mean, the long wave theory works for gradients to be small. Well, you may ask, okay, how small should be small? I don't know. But small, maybe, I don't know, maybe 1 is still small, maybe 2 is still small, but 10 is definitely not too small, maybe small but not too small, okay? So my feeling is that this film starts to grow because it's a solution. I cannot say, no, you don't grow, stay here. No, it's once you have your initial condition, it runs, okay? It goes by itself. It doesn't need to ask your permission, okay? So probably somehow we go out of the range of validity of this theory and without feeling this. So we don't have any cusps, we don't have anything, but somehow naturally this guy goes up. Once it goes up, of course, the minimal one should go down, and probably somewhere there, this kind of validity borderline is crossed. That's kind of my feeling, but maybe I'm wrong. So that's my explanation I gave to my student. My student is not happy with that, so he is thinking. Today is what? Wednesday, so he is flying to London to watch this game between two German teams. What is that? Borussia and Bayern. Okay. So he's probably thinking now about this. Okay, so let me skip this, and that's actually a summary because I'm sure that I don't have more time. So what do we have here? In the low frequency case, which I discussed here, so for a single frequency case and for double frequency case, of course, so we find that we can prevent rupture of otherwise a capillary rupture of the film, and for the single frequency case and for the case of isothermal, which I discussed only. So the borderline is given by this expression. B omega is actually constant. And in the double frequency case, it's certainly kind of unusual behavior with these spikes in the critical amplitude variation with respect to Chi. And what is interesting, I did not discuss that, but we can prevent rupture. Actually, of course, if you have two components in the double frequency case, if each of them is in its own single frequency non-rupture domain, there is no rupture. Now the question is, what happens if one of them or both of them are in their own single frequency rupture domain? What happens? Can you save the film's life? And it turns out, yes. You can be up to 30% below the critical line for the single frequency critical line in separately, and you can still, by joining forces of these two guys, you can save the film from rupture. However, we did not find any evidence if we can cause rupture by two components which are above a rupture line for each single frequency case, but it probably doesn't exist. We can prove it, but apparently it does not exist. And finally, we have this beating phenomenon, which is kind of interesting. The peak-to-peak size of the pattern grows, and it grows in such a way that for sufficiently slow amplitude modulation, the film ruptures, and that's exactly the stuff we discussed now. It's sort of terra incognita still, in spite of the fact that it seems that this kind of opinion that we probably are already outside the range of validity, apparently it's correct. Okay, so thank you very much for your attention.